So I'm going to walk through the main points of Lab 10, the last lab in the class. And this is a lot like the strain lab, where there's this nice excerpt from this textbook it's the same textbook as the strain lab. And so you'll recognize the format. And in this lab, all we're asking is for you to complete these problems in the boxes, and not all of them, only 17.1 through 17.5, 17.7, and 17.9. And I would emphasize that I've put a lot of guiding material on the Canvas website, so go ahead and check that out if you are struggling or have any trouble, and there might be some hints in there or links that will be helpful. So the first topic that the lab covers is the idea of plate boundaries, and in particular looking at triple junctions. So when you start dividing up a sphere like the Earth into small tectonic plates that are shifting around, a lot of them interact along their edges, and then we get these important intersections of edges called triple junctions, where three plates meet. And of course, the three main kinds of plate boundaries are convergent, divergent, and transform. And importantly, you can have a combination of these as well. In particular, you can combine transform, so sort of a shearing, strike-slip style shearing, with either divergent or convergent. So you could have convergent transform or divergent transform mixing, and that would be oblique. Now, transform, just like strike-slip or shear-slip faults, is split into right lateral and left lateral. And so to fully describe a plate boundary, we need to describe whether it is convergent, divergent, transform, or oblique. And if it is oblique, we should specify whether it's right lateral or left lateral mixing with the divergent or convergent, or and also if it's just transform, we should specify if it's right lateral or left lateral. So with that understanding, the idea at a triple junction is that we can look at two of the boundaries and determine, using a little construction, what the type of boundary is on the third boundary. And so for this construction here, I'll just make up some stuff. We'll say that A and B are convergent boundaries with no obliquity. And we'll say that A and C are strike-slip or transform boundaries with a right lateral sense. And then we're going to put some rates on here. So we'll say this one is at 4 centimeters per year, and this one's at 3 centimeters per year. That means that if you're standing on C, you look across at A, you'd see it moving to the right lateral sense, at 3 centimeters a year. That's how fast it would be moving. Same for B here. If you're standing on B, A would be coming towards you at 4 centimeters a year. And you can flip that. It's all relative, right? You can flip. You could say if you're standing on A, then B would be moving towards you at 4 centimeters per year. Our question is, given this information, can we determine what this plate boundary at this orientation between C and B, what its behavior will be? And we can. So the idea is we're going to draw a little diagram off to the side here, and we're going to pick a plate to be fixed to start off our diagram. So we're just going to make a point and say, we'll say that's C, point C. So this point is saying that we're going to fix the location of C. We're going to stand on C and look at how the other plates are moving relative to C. So one piece of information we have is A's movement relative to C, and we can say that that's right lateral 3 centimeters a year. And so we can take the orientation of that right lateral movement, so approximately like that. If you're standing on C, A would start here and go to the right. We can take that same movement and transfer it here. I'm just going to use centimeters on here to get the length, which will represent the speed. So that's 1 centimeter a year, 2 centimeters a year, 3 centimeters a year of movement of A relative to C. And so we label the tip of this as A. Now we got to get to B. So we don't know B relative to C. That's what we're looking for. So we're going to use B relative to A and build off of A. So if we say that A is now fixed, it's not moving, how is B moving relative to it? Well, we know that it's 4 centimeters a year, and B is moving towards A, so sort of towards the northwest here. So if I take that orientation and I just shift it over, and I draw in a 4 centimeter long vector. This takes us from A to B. It says that B, if you fix A, is moving towards the northwest at 4 centimeters a year. Now we've got everything we need to complete our loop. We're going to say, what is C's relative velocity compared to B? So we can just connect them, and it helps me at least to think about fixing one of them again. So let's say we're fixing C. Well, that means that B is moving very slightly east of north with a velocity of 1.5 centimeters per year. So I could label these. This is 3 centimeters per year, 4 centimeters per year, and 1.5 centimeters per year. So taking that orientation, we know that the arrows are going to be along that sort of orientation, and it's going to be, if C is fixed, B is moving towards the northwest, so this is actually going to be divergent oblique. So B is moving like that, C is moving the opposite way, and the velocity is 1.5 centimeters per year. So to fully describe the CB plate boundary, we would say that it's divergent because the two plates are moving apart. And then we need to describe whether that transform component to the oblique motion is left lateral or right lateral. So let's fix C, and so we're just looking at the velocity of B relative to C. We can see that it's away and to the left. And it works the other way too. If we go B, cover up B's arrow, fix the location of B, look at C, C is moving away and to the left. So the CB boundary is oblique. More specifically, it's divergent and left, actually I'm going to reverse these, left lateral and divergent. Typically we want to put the dominant motion first. So in this case, the majority of the motion, the larger component, is a transform motion in a left lateral sense. Smaller amount of the velocity is in divergence. So we'd say left lateral and divergent. Okay, the next couple problems get into focal mechanisms, which a lot of geologists sort of use a misnomer for. They call them beach ball diagrams. But it's important to remember that a beach ball is actually not a great way to describe these, because when we look at a quote-unquote beach ball diagram, we sort of, I think when I look at this, I imagine it pops out like it's a round sphere. But in fact, these are stereograms topographic projections, they're stereo nets, and they are lower hemisphere, just like we've been working with before. So when you're looking into this diagram, you're actually looking into the lower hemisphere, a bowl of a stereo net. So that's an important thing to try to not let your brain flip the direction of it being an upper hemisphere versus a lower hemisphere stereo net. And with that first very important fact stated, this is a pretty good description of stereo nets. I also linked a great little PDF from another university the professor made that describes stereo nets, and I think it's very complementary to this. It describes them in a slightly different way that might be a little bit more approachable to some if you're not familiar with this stuff. And the idea with constructing a beach ball diagram, a focal mechanism, is that when an earthquake happens, let's find the right figure, like this one here. So when a earthquake happens, for example, we'll say this is a map view, we've got our north arrow, and there's a fault running east-west, just a vertical strike-slip fault, right lateral. And when an earthquake happens right here at the epicenter, you can imagine that this part of the earth is going to shift right, because it's right lateral. This part will shift the other way. And that will set up a pulse of compressional and dilational seismic energy that move into these quadrants. And so when this upper half of the fault moves right, it compresses everything in B, this sort of quadrant B, and everything in A gets opened up, pulled apart, or dilated. And we get the opposite effect down here. When everything shifts left during the earthquake, we get dilation in this quadrant and compression in this quadrant as the rocks right around the earthquake here try to move. And out far from the earthquake, the rocks aren't moving. So with this idea that in different quadrants, looking away from the earthquake, we're going to see either compression or dilation, and that's shown in the seismic wave itself by whether the first movement in the seismic wave is up or whether the first movement is down and then up. We can actually reconstruct whether, for example, an earthquake represents movement in a right lateral or left lateral sense by mapping out these quadrants of dilation and compression. So when we do that, the best tool for mapping out those seismic waves as they travel out and whether they're compressional or dilational is on a stereo net. So what we do is we put a stereo net down at the earthquake's epicenter, and then we plot seismic stations as lineations, as points. And so these have a trend, an azimuth, and an inclination down, a plunge, that represents the direction towards the seismic station. And we just mark that dot with either a closed circle or a little open circle, depending on whether we got a compression signal there or a dilational signal. And when you plot a lot of these points from all the seismic stations around the earthquake that received energy, you get a nice quadrant pattern like this. And all we do then is just fit these two perpendicular planes to segment up our lower hemisphere projection into these quadrants. Now this is sort of the simplest case where we have a perfectly vertical fault oriented either north-south or east-west, and it's moving in a strike-slip fashion. This is the exact same setup as this diagram here. And so looking from above, we see these nice clean compression, dilation. But you can imagine this, if you flip the earthquake on its side and turn it into a dip-slip earthquake, a reverse or normal earthquake, then you're going to make a really different looking pattern. And the pattern you would start making is one that looks much more like this, where we've got our compression and dilation as sort of strips around the side of the beach ball, and you can imagine we would get that cross and clean quadrant shape if we looked down from this direction and looked onto the intersection of our two auxiliary planes. And so that's the first piece of terminology. This plane and this plane, these perpendicular planes that we fit to the data, they're called auxiliary planes or nodal planes. And they are both possible faults that could have produced the pattern of compression and dilation that we see. The difference is the sense of slip. So looking at this one, if in fact the north-south fault is the fault that slipped, we can look at what is the sense of slip here. We can see that there's compression and dilation. So that means that this side went towards compression, this side went towards compression, and we end up with a left lateral sense of slip. On the other hand, if we have this being the true fault, then we look at the north side and we see that compression is here, so we get right movement. Down here we get right movement, so that's a right lateral sense of slip. So depending on which of the two nodal planes the fault was actually the earthquake actually occurred on, that would either imply that it's either a left or a right lateral fault. Now, a good way to remember which way slip happens, if we pick one of these nodal planes and try to remember which direction the arrow goes, either from the dark to the light or the light to the dark, I always think of what that handout actually says, which I think is a really catchy way to remember it, which is come to the dark side. Think of Darth Vader from Star Wars. The light side, he's always asking it to come to the dark side, so the arrow would always go towards black. They're not always labeled compression and dilation, so that becomes helpful when we're looking at a diagram like this, where here maybe we can't remember which one's compression and dilation, but we can remember if this is our fault, come to the dark side of the force. That means we're going to have an arrow moving that way, right lateral sense. If this is our fault, it'll be towards the dark side, left lateral in that case. Okay. So to figure out which of our two nodal planes was the one that ruptured during an earthquake, we have to use some additional context and information to narrow it down. We might have field information that tells us that in this area where the earthquake occurred, we only see faults with a single orientation this way. And so we could say, okay, it's probably that one that ruptured, not this perpendicular one that we don't see represented in the field. So the first task is 17.3, which says look at figure G58 and basically figure out what are the possible faults and earthquakes that have been given these focal mechanisms. So here's figure G58, and we've got three focal mechanisms, and it's also given us, just for reference, a blank sterionet with some representative dips for different great circles representing different planes, and we can use that just to estimate how much our nodal planes are dipping on these figures. So let's work through one of these. We can work through A. I think it's a good example. So A has two nodal planes. We've got this one and this one. And so already we can see this is not a pure strike-slip earthquake. If it was strike-slip, it would look more like this diagram, where it was basically just quadrants with a cross. Here, it's definitely going to be oblique. We see the intersection of our two nodal planes, and so that means it's not purely dip-slip, but there's this large dip-slip component represented by these big regions here. And it's probably good to just memorize this, because it helps you sort of quickly identify what's going on. But any nodal or focal mechanism that has dark on the outside and light on the middle, that is a normal dip-slip focal mechanism. This is the opposite, where we have light on the outside, white, and then black or dark in the center. That represents reverse slip earthquake. Okay, so that was a bit of an aside. The first task is to determine the orientations of our two nodal planes so we can give our two possible fault orientations. And then step 2 is to look at each of them and say, what would, if that was the nodal plane, what would the slip sense be? So this upper nodal plane, it is, remember to imagine this is our sterionet, lower hemisphere projection. So I can look at this and say, the strike is like that, and it's dipping down to the northwest. And for this, we're just going to estimate. My guess is it's not like 45, it's probably a little bit steeper, maybe 50 degrees. You can use this for reference as well. It's like, 50 degrees seems about right. So this is dipping down 50 degrees to the northwest. So I'm just going to draw that as, we'll call this one 1, I'll do this one as 2. 50 degrees towards the northwest. That's fine notation. Just dip in dip direction, approximated. And we need to get the other one. So the other one is 2 striking this way, dipping down to the south-southwest. South-southwest. So it's going to be towards the south-southwest. And it looks a bit steeper, and so I'm going to say it's more like 60 degrees. Just estimating. A little bit more than 50, a little less than 70. Something like that. So now we need the slip senses on these two. Okay, let's look at fault 1, or nodal plane 1 first, dipping down to the northwest. I think the best way to think of this is with this black on the outside, white in the middle, to get the overall sense. And so in this case, this is going to be a normal fault, but with some oblique, strike slip component mixed in. And so let's look at, we're looking at 1, so we're going to start with that as our fault. Zooming in on the orientation here, it basically just becomes like one of these more upright faults that we've done before. So again, we realize this is our fault, fault 1. We need to know what Darth Vader says. He says, come to the dark side. So this is going to be there and there. And we can see that that is right lateral around that fault. So this is a oblique fault with a right lateral normal sense. And the other fault plane, so now looking at this fault plane, I'll just kind of draw over that stuff, we can see that come to the dark side, our arrow is here and here, and so that indicates a left lateral sense. So that will be left lateral normal. Okay, so that was the analysis here. You basically take the overall look of it. So in this case, we had white in the center, and so we knew it was a normal fault. And then you take a look at the intersection, if you can see it, to get the strike slip component, showing that it's oblique. If you don't see the intersection, if instead your focal mechanism looks something like that, not very well drawn, and the intersections are right on the edges, that tells you that it's a pure dip-slip fault. Basically, we could say this is, so it's dark in the middle, this is a reverse slip fault, and we would just give the orientations of our two planes, both of them being reverse. Okay, I'll let you go ahead and try out the other two. So the final two questions on focal mechanisms refer us back to our first figure here, looking at the triple junctions. and it just asks us to sketch focal mechanisms for each for earthquakes that would be expected to occur at each of the plate boundaries in 17.1, 7.2. And it wants you to label the fault plane and the auxiliary plane and then the P and T axes. The P and T axes are pretty straightforward. They are just axes in the center of their respective quadrants. T for tension is in the middle of the compressional quadrant, the dark quadrant. It's a little bit backwards from what you might expect, but read about it. It actually talks about why that's backwards. And then P is pressure, and that's in the dilational quadrant in the center of it. So looking back at our triple junctions, let me get my example triple junction. So here's the example one I just made up. We can start with the CA fault, and that's one way you can refer to these. It's just like the CA fault, CA, and it's a right lateral strike slip, pure strike slip fault, and it's, you can draw these focal mechanisms relatively small. This one's maybe a little too small, but I'll go with it. You can see that one of our nodal planes is going to have this orientation, and it's going to be the fault. So just sort of copying that orientation over like that. And then perpendicular to that will be our auxiliary plane, the non-fault nodal plane. And now we just got to fill in the dark and light. So this is a right lateral sense. You can think of it how you want. Go to the darkness, or also just the fact that this would be compressional in this quadrant. As stuff moves in, this would be compressional. And we've got our solution for an earthquake occurring on this fault. Now, it asks to label some things, so you probably want to label this like that as the fault plane. You could simplify this to auxiliary plane, AP. And the axes are going to be right on the edges because we're looking right down on the intersection. So this is going to be our tension and pressure axes. Okay, 17.5 asks us to plot a focal mechanism based on seismic data shown in G59. So if we pull up G59, that is this figure from the appendix. And normally we would plot this on a StereoNet plotter with the usual tracing paper, etc. So we're not going to be able to do that. Most of us don't have access to tracing paper. So instead, I suggest that you tackle this problem using a computer, plotting the figure using Allmendinger's StereoNet program. That's probably the one I would recommend. You probably would be able to do it in Visible Geology, that sort of applet in a browser, but Allmendinger's StereoNet program is definitely going to be a little bit more powerful and maybe less frustrating. So let's take a look at that. Okay, so here, back on the Canvas website, we can tackle 17.5 with this Excel table I've included. So we download that file, open that thing up, and this is what I made. I just digitized the information in the appendix there. And a couple of things need to be done. One is that if you read in detail, and this actually caught me up the first time I did this problem, an important detail is that inclination or incidence is not equivalent to plunge. for plotting on a stereo net. So what you need to do is convert incidents to plunge. And so if we just shift those over, we call this plunge. I can zoom in so this is not so tiny. Okay, so we make a column for plunge, and we just say that it's equal to this, actually 90 minus that. So the angle of incidence is the angle from vertical. What we want is the angle from horizontal to give us a plunge to enter into the stereo net program. And doing 90 minus that will give us that value. Okay, so we also want to make two separate data sets, one for A and one for event B. So over here, I'll make our event B data. So we'll just copy this all here, and I'll delete A from this. And actually, I'm just going to get rid of these other columns. Whoops. If you have that problem, copy the whole row and then paste special values. Now they won't disappear when we delete the referenced thing. Okay. Cool. So this simplifies things. We just got azimuth, plunge, and the event type, compression or dilation. Just repeat that over here. Copy all these. Add these on there. Fix my typo. Okay, so we've got our values. I'm going to save this as event A and just save it somewhere accessible. Okay, and importantly, save it as a CSV so that we can import it. I've done this once before. Okay. Do the same with our event B data. Event B data, CSV, save. Okay, so now we can close both of those. Oh, actually, before we close them, back up here. We're going to do one thing just to make our lives easier. And that is select these and go to data, sort based on event B, and that will organize these so all the C's are together, all the D's are together, etc. Data, sort. Alright, save that, close, close. Okay, we can open up stereo net. And new blank window. And we're going to import our data. So import text file, group event A data. There it is. We'll start with event A. And our import window pops up. So it looks like this, and this is where we're going to be tricky. So first of all, we can label, we know that the trend is 1, the azimuth, and then plunge is 2, we calculated that, and we know we don't want the header row, but I'm actually just going to import all the C's. So I'll scroll down and find where the D's start, the dilation, and we just uncheck all of those. Great. So now it's just the C's. I'll hit OK. And up here, when it creates that data set, I will make sure I put C into there. So event A, C. I'm just going to repeat that. Import event A. Uncheck the header row. 1, 2. And this time, uncheck all the C's. Leaving just the D's. And uncheck the N's as well. Okay, nodal plane ones. Great, and then rename that one D. And we'll add one final I'm going to import all of those 4 orientations that are N nodal. That if you read the on the assignment, it says that anything with an N basically didn't have a very strong dilational or compressional first movement, and so then they just get an N. Or if it's very weakly compressional or dilational, it would get a C or a D. We can just have these all just be nodal planes. So these are going to be near, hopefully close to our nodal planes. All right. 1, 2. So I'll call that N. Okay. Here's the magic. Inspector. Open up our inspector under View. And under Data S ... I'm guessing data set. I don't know. It's cut off. We're going to color each of our events by to make them a little bit more visible. So I'm going to make them bigger, make them 5. And remember that compression we usually want dark, so I'll leave it black. And then move on to dilational, which we will make bigger, but we actually want it to be hollow. So now these hollow circles are all the dilation. And then finally the nodal ones will make 5. I'm going to make them gray, just to be in between. And I'll make them triangles. Okay. Great. So now we've got all of our data plotted up based on compressional, dilational, and then these nodal planes. And our job now is just to fit some nodal planes to it. In StereoNet here, if you hold Option or Alt, you can, I'm sorry, not yet, I guess. Here, we choose New Planes. We'll call them nodal planes. And enter with mouse. By going down here and right-clicking, enter with mouse, that turns that on. Now we can Alt or Option click, Alt on a Mac, or Alt on a PC, Option on a Mac, and you can click and hold and draw in a great circle. And so we want to just fit our great circle to divide up the data. And I've now got my 4 quadrants, and I can determine, using these 2 possible orientations, what was the most likely of the Mendocino triple junction faults that this slipped on. Repeat this analysis for Group B and take screenshots of your final solutions like this. All right, so the next question, 17.7, asks about magnetic anomalies in an oceanic plate, and it's a simple little geometric problem about spreading rates. And the idea here is that if we cut a cross-section through a spreading ridge, we'll see something like this, where we've got our spreading, and these are our two pieces of lithosphere spreading away, cooling, like a conveyor belt, and we're producing new oceanic lithosphere here. And the idea is, as these move away, they create a barcode of magnetic stripes that are mirror images of each other. So every magnetic polarity switch that reverses the polarity of the rocks being made at the spreading ridge gets split, and we have a mirror image of that polarity chron spreading into each direction. I'll try to draw these symmetrically. We'll put a really big fat one here. And so they correspond. And the terminology it uses here is, it says anomalies number 12 and 23. And so the idea is that these are typically numbered. And an important thing is that, as always, it's mirrored. So one on this side has an equivalent on this side, and it just marches out. And it gives their ages. So anomaly 12 is 34 MA, anomaly 23 is 52 MA. So let's just do something similar. We'll say that anomaly 3 here is 6 MA, the rocks at anomaly 3, and at 7 out here, the rocks are 20 MA. I'm just making up different numbers. The idea is that the measurement we've been given is that the two anomalies on a single oceanic plate, that's why I've drawn them both on the same oceanic plate, not the other one, they are 810 kilometers apart. So this distance is 810 kilometers. So for the purposes of my little diagram, I'll just make it 400 kilometers. Just to change the number so that you have to do the question. Okay. What is the time average rate of spreading across the ridge during this interval? So it's asking, what's the spreading rate on the ridge? And that, importantly, means that it's as if you were standing here. How fast would someone standing on the other side be moving away from you if you fixed one side? And so to get that, really what you need is the rate between 2 points that were once both at the center that have now spread apart on each plate. And so if we go over here, we find 3, this is our 6 MA point, 7, this is our 20 MA point. What we can do is draw a diagram where we've gone back in time 6 million years. And what we end up with is now anomaly 3 is here in the middle, and we've got and this is now no longer 20 MA, since anomaly 3 is now at 0 MA. We've gone back in time. This is going to be 14 MA. We subtract away 6 MA. And we still know that this distance is 400, and this is 400, and so the overall distance is 800 kilometers. We double it. And so what we can say is that the spreading ridge went from a width of 0 to a width of 800 kilometers in 14 million years. If we convert that down to millimeters per year, I mean, you could report it in kilometers per million years. Just divide that value. A more common value might be millimeters per year or centimeters per year. but just divide that value and calculate it down, and that gives you the spreading rate for this ridge. And the last problem on the lab is problem 17.9, the plate game, and it refers to G61, this appendix, this complex looking thing, and it says that the appendix is depicting a present-day configuration of some hypothetical continents and oceans. The map contains geologic information as well as seismicity, a bunch of other geologic data, and we've also got these important magnetic anomalies. So here they are. These are plots of magnetic polarity, and you can see that we're switching between normal and reverse polarity along these lines, and these are from transects across these oceans. So A is up here, A to B. You just fit that line right along there. And that's all the data we've got. So the other thing we've got is this table summarizing paleomagnetic inclination data with some radiometric ages. And this requires just a little bit of work by you. If you go back a few pages in the textbook, you will find on page 160 these equations. So this equation is I equals, these are equivalent, they're just reorganized to move the lambda or the I inside the equation. But this is relating the inclination angle of the magnetic data to lambda, which is the latitude. So tan inverse of 2 times tangent of lambda gives you the inclination angle. And then the same formula, basically, except instead of multiplying by 2, we divide by 2, gives you the latitude if you have the inclination. So apply those formulas to convert these inclinations, I, to these latitudes. Is that lambda? Yeah. Lambda. Fill them in here. Okay. Once we've got that latitude calculated, then we've got all the data available to us. So it says that additionally we can assume that spreading in oceans is parallel to the transform faults and perpendicular to ocean ridges. That's just to say that if we've got a spreading ridge, they will be perpendicular to these transforms, and spreading will take place like that. So we're looking for this kind of geometry in our spreading ridges. 1. Outline all the plate boundaries using all available information. Name each plate or tectonic feature for use in your discussion. Be creative, so you can name some geologic features. Fix one plate. Describe all the other plate motions in terms of the fixed plate reference frame. This is similar to what we've been thinking about in those triple junction problems. And then write a plate tectonic history of the region shown on the map, and try to include all of the geologic and geophysical information. So I would encourage you just to give it a try and use all the data however you can. I'm not going to give too much advice on this, except to say that the thing to look for in the geophysical data is symmetry. So, for example, on AB, I see a very indicative little symmetrical sort of flat bit with some little horns on the side, and I would divide it, the symmetry of it is around this line, and so you can see everything on the left of that is symmetrical with everything on the right. And you'll notice it's not in the middle of AB. So this would suggest that our spreading ridge is spreading from this line outwards, and that it's closer to B, the spreading ridge, than it is to A. So when we look at AB, we can kind of look at that proportional distance and say, oh, okay, looks like the spreading ridge maybe is around here. And useful to see some other data. So here we have a focal mechanism. This is a normal faulting mechanism. So we might think that the spreading ridge would go right through that. Looking in the other direction, we see a active volcano. Spreading ridges are volcanoes, and so yeah, you might expect a volcano along there. And this also predicts that we should see a spreading ridge around the center, maybe a little closer to B, on CB. And when we look at CB, we see that there's symmetry right there, and it is about symmetrical, maybe a bit closer to B. So that's all adding up to saying that, oh yeah, there's a spreading ridge coming through here. Continue that logic to try and wind around the spreading ridge through the ocean here using these lines and some of this other information. And you'll be well on your way to setting up the divergent boundary in that ocean. The other piece of information that is a little tricky to use is this Paleomag data. So the idea here is it tells you, most of these at least should tell you, yeah, they're all paired up. So P1, P2 is paired, P3, P4, P5, P6. So we can look at P3 and P4, for example. That's right here, P3 and P4. And what they're saying is that at 15 MA, the latitude was whatever you calculate here. While at 2 MA, more recently, it's changed to here. And so let's say this is 40 degrees north, and this is 33 degrees north. We're not north or south, so. Yeah, but it's okay to assume that these are all north anyways, because we've got our north arrow. But regardless, this shows that from 15 to 2 MA, this point right here moved from 33 degrees to 40 degrees. It moved farther north. It's moving this way. And so thinking about the faults that are around it, and the plate boundaries, and how you could accommodate that motion, as well as comparing it to other paleo sites, paleomagnetic sites. So here's P5, P6, and P1, P2 way up here. That is a great way to get at some actual time constraints of when different continents drifted apart or together.